Right, I'm going to begin with the introduction to Oregon geology and material logging. My name is Sean Finn. I'm the Oregon Water Resources Department in the North Central region, well inspector for this region. So, previous well inspectors have made these presentations in the past. From what we understand is there are some ways that it can go wrong when understanding this information because geology takes a lot of observation and making sure of what exactly is seen in each of the well clippings in order to get a better understanding. And so when looking at all of this information, it is very important to document all of the materials that are being observed. All right, so our objective for this talk is to familiarize everyone with some basic rock types. We need to cover some of the basic Oregon geology while doing this, so that everyone has an understanding of what Oregon geology is like and what can be seen when drilling at depth. And to discuss some of the basic logging terminology and techniques in case you are ever asked or in charge of logging it, which you would as you drill. Last, we need to relate this to what are the rules in Oregon's well construction. All right, so when doing some observations of rock types, it's important to remember that all rocks are made up of minerals, and these minerals have a story with how they interact with the earth, whether they're eroded and become sedimentary, whether they're melted and form together, in which case they'd be igneous, or whether they're just shaped but not fully melted, and that's metamorphic. And so those three rock types are the changes that are happening to the mineral types within these rocks. So there are three: sedimentary, igneous, and metamorphic. You may have heard these ever since you were back in grade schools. These would be talked about. And most of Oregon is made up of two of these. You have a lot of sedimentary and igneous, but the mountainous regions are really where you would see the metamorphic types. So just some side notes. I am more of a geophysics type, which is kind of the nature of each of these rock types, and less of an actual geologist. However, I may be able to discuss how these would be formed. So let's get started with sedimentary types, because this is what is so common throughout reworked basin sort of fills, where you might get, or you would have these drilling of the wells. Sedimentary rocks are formed from lithification. So the term lithification just means the hardening of the rock, basically. It is compacted during this process under pressure. So whenever you're piling sediments and everything up on top, when I say sediments, these are broken down rock that is maybe moved from mountain areas to the valleys, or it can be moved along rivers or through wind. So when all of this broken rock is regathered into an area, a basin, an area where it's going to kind of pool, these get pressurized as they layer up on top of each other. And this layering process is really the main observation when looking at outcrops of sedimentary rocks. But you don't quite see this maybe when drilling. Sedimentary rocks are formed from loose sediments, the things that are washed away, that have been buried, and as a result of this pressure, the grains kind of come together as a cohesive unit. Okay. In Oregon, for example, the T formation, which is made up of turbidite sequences. Turbidites are where you're going to get a wash, usually from like a coastal area, them dropping down off the coast. Basically like a landslide. So in Oregon, that would have occurred with the Oregon coast. And so this turbidite sequence, so it's just a sequence of a landslide or a wash under the ocean, was then buried and accreted to the coastal range. So along the coast of Oregon, you would get these sediments compacting, layering one turbidite would fall off and then be stacked by another, and then stacked by another, and stacked by another. And that much weight on it is going to form that lithification process. It's going to get that process really started. Here's an example of how you might see a sedimentary. Here's an example in this case of the T formation. And this was given from one of the other ones that was presenting on this information. But in this, you can see kind of how in sedimentary rocks you get these different layerings, okay? So off to the left, kind of above where this person over here with the orange hat, he's seeing that you have these fine layers, and then some of the layers are bigger, and then some finer layers. And notice how not all of them are lithified, hardened into the same form. Some are like a section, and other ones look like they're falling apart or washing off themselves. And so that's part of the sedimentary rocks. Sometimes the lithification process, what's called cementation process, doesn't necessarily hold the rock together. And so they can become unconsolidated and can easily break and fall apart, or allow for different types of fluids or other things to move throughout it. It can also lead to a process where, like when in a well case, you would have a collapse of the walls of the well because of this unconsolidated sediments. Whereas a consolidated sediment, something that's a more hardened, generally maybe would have less porosity or permeability, and so they would be more compacted, held together, what would be called accreted. So each band is likely a discrete event of slope failure. So each time you're seeing a different layer, those are different events that are taking place. They didn't necessarily all occur simultaneously. Okay, the next type is going to be igneous. Now, throughout the state, there's large igneous provinces, what are called usually the Columbia River flood basalts or some other flood basalt areas. But there are other kinds of igneous rocks, some related to volcanics, other related to plutonic, basically the throat of a volcano that has now been eroded to the surface. So if we take a look at some of these igneous rocks, you can see when you're looking at them that some of them have textures inside them. They have little dots, blacks and white colors, and other ones are completely composed of a single color. This has to do with not necessarily a grain size, but more of a crystal size. And it generally gives us an idea if a rock, when it was formed, was cooling externally, outside of the earth, or internally, within the earth. So igneous rocks are formed from the melting of mantle materials, melting of earth materials. The various differences in igneous rocks comes from two different types of things. One being the silica content, okay? Now, most of the earth is, the rock types are made up of silica. Silicon within the periodic table, there can be incorporated other things, irons, magnesiums, things like that. But silica is so important within rock. The other part of it is how extrusive or intrusive it was. And further for that, how much time did it have for that to allow for the crystal formations to form? Meaning, was it erupted from a volcano where it would be probably ejected out of the volcano and cooled very rapidly, and so the crystal size would not be quite as large? Or did it cool deep underground, where this cooling could happen slowly and the crystals would have time to grow and really form? And so if you're looking at some of these pictures, like this one that says diorite, you can clearly make out the differences between the crystals, the blacks and the whites. This is giving some indicators that it cooled internally. Even the gabbro, where the spots look like dots in it, but it's still easy to see. Compare that to the basalt, And basalt is cooled externally. It is erupted from vents, usually not necessarily a volcano, but more of like um, little lava tunnels or other sort of areas. And these basalts would cool very quickly relative to everything else. And even if they cooled within a few weeks' time, that's fast. That's very fast geologically. So that gives you an idea of what you would be seeing in these different types of rocks. Okay. Granites, for example, on this image, there's kind of the granite down here, and this granite has some makeup of the crystals. You would usually see these as maybe like a red color and some blacks, or some whites and some blacks. But all of that is dependent on how much silica is within this. So these granites have discrete minerals that are visible in the rock, whereas basalt, which was cooled externally, does not. This is because the basalt, which cooled quickly, is freezing in something called amorphous. So if the idea would be like it morphs, it changes to show this. It didn't morph. It didn't get to show the crystals. It was amorphous, without form. While the granite cooled slowly in the underground and at a much slower rate, where each of the crystals could form and grow at their given rate. Volcanism comes in two main drivers. There are hotspot volcanoes, such as in Hawaii or with Yellowstone, for example, or there can be plate boundary volcanics, much like Cascadia. A mountain range is formed along the whole ridge of North America, and these volcanoes, St. Helens, Rainier, Baker, all of these are going to erupt, but most of the other times they stay kind of docile and calm, and then all of a sudden big explosions. This can range all the way down to Mount Mazama or Crater Lake in the south of Oregon, where the explosions can be quite instantaneous and big. They may not erupt like this all the time, but it still is an eruption that has effects for the area. So if we take a look at some of these visuals, you'll see just what a basalt colonnade structure looks like. And if you look in this image, you can see this person climbing up these colonnade structures. These columns are formed because they're part of the cooling structure of these large, basically lava bodies that are moving over the landscape. Internally to them, so the columns are generally towards the outer parts. Internally to them is something that we would term as the entablature structure, the inside of the flow. But these flows are going to form, and it indicates that this was like one tube of lava on the inside and some colonnade structures towards the outside. And then you usually get the process to restart. This is showing one large process, and then below it is something else, so a different flow. This is an extrusive lava flow. These columnar jointings, these colonnade structures, columnar, column, jointing, physically jointing is just how any corners would have formed, which is the cooling fractures that are perpendicular to the cooling surface. Okay, so you see these lines of them going down, these columns. They're cooling towards the ground or towards the top. This is why you never throw hot water on your windshield when it's icy. When there's dramatic change in temperature, you'll get fractures and cracks. These columns, these fractures from that are formed. You can often see these features when driving through the gorge or as far west as what's called Seal Rock State Park in Newport, Oregon. One of the big flows is the Columbia River flood basalts. These are through the central, northern Oregon, all the way up into Washington, with distinct flows also towards Boise and Yellowstone. All of this may be interrelated. Okay. Large intrusive igneous examples can be gigantic. These are plutonics. The term plutonic actually comes out of the history of geology. There were geologists that thought that heated material within the earth could actually extrude itself to the outer part of the planet. These were Pluto-based sort of ideas back then, they called it. And so we have terms plutonic compared to some of the other forms that thought the earth was without changing, which was just perfect in its form. So now we have these terms for the exposures of the throats of volcanoes that have been churning out magmas and lavas through time, but have cooled down and formed their crystals. And these crystals can now be seen on the surface because the volcano structure, or wherever these were coming out of, has been eroded away. Here's an example of an intrusive igneous rock. This is showing Yosemite National Park. As you can see, the large, all of it looks the same, but there's some components that look like big boulders that might slide down the mountain. Yosemite is what is called a batholith, plutonic, a relic lava chamber that fed volcanoes. In this example, the extrusive erupted material has long since been eroded off the top, and the deeper, slower cooling materials are uplifted into a rebound. So it's like an idea to kind of imagine this would be like an iceberg or something, where you have all of this hard, heavy rock, and with layers on top, it weighs it down. But when you erode the layers off the top, it can rise up because it has been lightened. That's kind of the process that you would maybe imagine this. A way to kind of see this a little bit more up close is really right here. You can see kind of the crystal structures, and you can see which parts were interrelated. So some of these cooled faster where others cooled slower, and you can truly make out the incorporated crystals. So like you can see how this black one is including parts of this granite or other sort of rock, and so they can kind of feed on each other and remelt or incorporate. And this ultimately leads to where you get to a metamorphic rock. How do you change rock? So metamorphic rocks are changed rock. They're not as common necessarily in the west part of North America and thus Oregon, but the mountain areas can have these. So they're formed from existing rocks, other metamorphics, sedimentaries, or igneuses that have been reshaped. In Oregon, the metamorphics can be found in the May Creek schist formation in Jackson County, and in various areas of Strawberry and the Blue Mountains. So you have high temperatures and high pressures that can ultimately cook the rock again. It's not remelting, it's just reshaping it. And so you'll often get these like banded formations, but they're not like the grains that have all layered into each other like in a sedimentary rock. They're like crystals that formed in bands. It's a very different sort of look to it. This formation of these lines are these lineations, penetrative fabrics. So if we were taking an example of what you might be seeing, you would start out with like this granite, this speckled white and black. We know it's granite compared to maybe in one of the other images you saw that diorite, because of how many of the little black crystals are in this, which is having to do with that silica content. The more silica, it's just a different rock in the igneous. So on this side is igneous, but notice how it's been changed. How these fold lines and everything, these foliation lines, are all wrapped around, but the colors seem to line up. This is an indicator of a metamorphic rock. The rock has been recooked. Okay, it's moved through its lifetime. So you're seeing two different parts of the rock cycle here. In general, an understanding of this would be like from here. All rock starts here at magma. There's a cooling process to the igneous rock. Igneous rock can then be reshaped into metamorphic, or it can be broken down by streams, water, ice, wind, into sediments. Okay, so you have two of those. If you remelt it, it goes back to magma and can stay in this cycle over and over and over again. So let's go sedimentary, because that's what a lot of the state's going to have. So you weather it. River can work on a rock area over time, constantly eroding it, breaking it down. The bigger the grains, the closer it was to where it was broken from. The smaller the grains, the more it has been eroded down. Also, how rounded the grains are tells how far it's been transported. So it gets over here to sediments. The sediments can get compacted and re-eroded and compacted and re-eroded, and this process usually continues over and over. And so you would see like sand beds that are in some dune areas out by the coast. The whiter the color is, the more quartz, silica rich it is, and so the more it's gone through this process. Whereas our sands along our beaches in Oregon and Washington areas are usually a darker color, not necessarily a pure white, maybe kind of a yellow to a brownish color. That indicates that they have recently eroded off of mountain ranges and washed down from them. All of this process can then move on to metamorphic. So from this diagram, you get kind of the idea of the rock cycle. So this should clarify kind of what you're seeing in general of rocks. All of these things you have to look at. You have to be looking at, is it all connected together, or can you look at it and see grains? So if you can see minuscule grains in it, then you're probably looking at a sedimentary rock. If these aren't really grains but are grown crystals within it, you're looking more at an igneous rock. If you can't really see anything and it all just looks like a black, maybe like a basalt, that's the igneous type. So you really have to break it down to what you see. Now, it kind of helps that some areas of this map of Oregon have certain parts. So there are various geologic provinces. There's the coastal range right here that's made of accreted terrain. So accreted would mean to accrete something is to add it on. So there are terrains that have been added onto Oregon with time. The Willamette Valley coming through here is been topped. Those accreted terrains have been topped with Missoula flood basalts that have come all the way from Montana. They've washed through Idaho, through Washington, come down along Columbia, and washed all the way to the Willamette Valley. And you'll see so many things from that area actually indicate this washing. A large meteorite was found in the Willamette area. It actually impacted Montana. It's like the 6th largest in, I don't know if the world or our country, but it is quite a sizable meteorite, for example. The Klamath Mountains are made of metamorphosed accreted volcanics. So the Klamath Mountains are down here in southwestern Oregon, and this is going to be accreted terrains, but it'll also been volcanic. So you're starting to get the interplay of things you might see with like Mount Shasta and those sort of large volcanics down there. You would also get what is called an ophiolite sequence in that area, where seafloor spreading would have moved continents apart. Well, those parts that are formed at the seafloor spreading actually got pushed up onto our continent. Usually they're pushed down under our continent. You have the high and the western Cascades right here. The high Cascades and the western Cascades are made up of younger volcanics. So like Mount Hood and the volcanoes going down here all the way to Crater Lake and down towards Mount Shasta in California. Those are all those volcanics. Recent activities, releasing igneous rocks. Or igneous rock is exposed when the wet erosion of the batholith or Pluton happens. You have the Deschutes Columbia Plateau, which is made up of flood basalts. Okay, so down here, flood basalts again. Blue Mountains are uplifted rocks, so oldest rocks of Oregon are out in this area. You have the high lava plains, another kind of like flood basalt sort of area. The basin range, which is dominated by abrupt changes in elevation, alternating between narrow, faulted mountain chains and flat, arid valleys. And the Owyhee uplands in this form are dominated by lava beds and craters and cinder cones. So you're seeing a lot of volcanics actually across the state. As you can see, the state is made up of lots of different rock types. They're all shaded throughout this. Each one in a geologic map is termed to a certain type of rock, whether that's igneous or sedimentary, some even metamorphic, and you can see how distinct areas of the state have very different changes in those rocks. There's also these black lines which are showing the types of faulting that's happening across the state and the things that might cause earthquakes or just change and shift the rocks. As you can see here, you have some of the flood basalts. Out here is in the Washington, Oregon area, the Columbia Basin flood basalts, that shifting all the way down to southern Idaho areas, with lots of other sort of basalts in the southern Oregon area. When thinking about how rocks are formed, they have formed periodically and in different ways all across geologic time. Geologic time can be lumped down into this sort of scale. A lot of this was based on fossil record, but is now based on actual age dating techniques. So this ranges all the way from the formation of the Earth in the Hadean to the current times in the Quaternary. And you can see how it's broken down. So let's go over some introductions to the material loggings to get an idea of this. So discrete sampling is where each of the parts are each sample is grabbed and contained in its own set what the lithology is. So an example would be to walk over to a diverter pipe, sticking your hand out and collecting a fist of that material. You'd be able to look, is it sedimentary, is it igneous? Composite sampling combines a number of discrete samples from the same unit at various depths and combines all the samples for that unit into one. Basically, think of a composite sampling as getting the average material of that lithology. So you're looking at it and saying, okay, all of it seems to be sedimentary, okay, it's all finely grained, okay, it's maybe like a clay or a silt, so you could go and maybe say it was a siltstone, or how broken it is, how compacted and it held together. If you commonly drill deep irrigation wells, you might have collected these cuttings. Either way, when you're collecting drill cuttings for the department, it is always best to talk to your local well inspector or groundwater geologist about what method they prefer in order to understand. Often we can supply bags or Sharpies if you would want to collect samples. Okay. Giving the color isn't always the best indicator for the rock type, but it can help if other people are identifying rocks and minerals of a given area. These next handful of slides are going to talk about the sections of the Oregon Driller's Field Guide for Soils and Rock Formations. The color is always a useful tool in the material description, so actually describing this when writing it down is important. If you do not know or cannot tell the rock type, describe its cuttings. Give what indicators it has. Can you see individual clasts, individual grains? Are there minerals? Does it look like there's crystals? Things like that. If you rotate it in the sun, do you get reflections? Minerals often will reflect light and sparkle. Okay, hand lenses can help. If you look at grain size, you can see, is it fine grain? Is it coarse sand? Is it a gravel? Is it a clay? Okay, these are all discrete ways of looking at the geology of that actual area. These are good things to note, so when writing it down in your notes, you should always put these. Most drillers work in the same areas of time and time again, and so they know what the region has. When putting together everything, you need to identify, is there bedding of the layers? How cemented is it? How fractured and easily broken is it? Is there interbeds or tills? And how weathered or rounded it is. Okay. So when noting this, a best thing to remember is that Oregon has a revised statute here that goes and says that the kind and nature of the material needs to be listed. The kind and nature of the material in each stratum penetrated. At least one entry from each change in the formation, and the thickness for each aquifer. Okay, so when looking at this, you would see that each of the rocks are laid out with depth indicators for where those rocks are. Okay, so some rough logs when doing this should be listed like in this form, being consistent in the material description, using areas to indicate what the rock type is, what the color is, giving some ideas of other notes that you might have. So the above and beyond what is written in the slide, think about a rough log as a dialogue. Okay, think of how you could best use those indicators to describe it to yourself and know what it is. It helps to maybe have dates and times. So some other examples of this would be right here, where you might describe a date and a time when something happens, when drilling happened, at what depth, some indicators that are going to best help you describe overall what is actually being observed. This can often be done or seen in how geologists collect field notes. So there's going to be some observations at given locations. You're going to put down what types of areas of rock are around those locations, what types of observations are made of like rivers and things like that around an area. Well, with a well that's being drilled, you're going to take what the rock type is, how easy it is, how broken it is, how smooth each grain is, water, whether it's there, give all the observations that you would have on this data. Okay, the big takeaways in all this is to know that there are 3 rock types, and when looking at each of these rock types, it's important to note that they're different in how they're formed. Igneous rocks are formed from melting that is cooled. Sedimentary rocks are formed from the breaking up of any other type of rock that is eroded and weathered and migrated. And then metamorphic rocks are kind of like recooking something. Not melting it down again, just making it form in a slightly different way. Always note the geology and the major aquifers of the area. And when logging, give the material and drilling actions that best describe the local geology as noted while drilling. So being careful to notice kind of colors of the grains, how weathered they are, how changed they are, how whether they are the same type of grains or different type of grains. In overall, just be consistent. Just note it, know the depth, know as much evidence as you have, and compare that to how other wells in the area have been drilled to know if it is consistent and matches those. Oregon is a very diverse state, both geologically and hydraulically, I should say. So being careful with how the logs are made is very important. More notes on the rough log is always better. So while doing the drilling, make an observation sheet that has the most details, and then actually on the well log, just the parts that are needed, and go back to your report if need be. Any questions or comments? Okay. Again, I am Sean Finn. I'm the North Central Region Well Inspector. I can be contacted by email or by phone if you have questions or need any help. Thanks.